In this video, we're going to look at some of the results from our angular acceleration lab and think through what kind of conclusions we can draw from those results. So just a reminder, our purpose in this lab was to determine the relationship between the torque exerted on a system and the system's angular acceleration. So we had a lab apparatus made up of PVC pipes and it had wood hanging off of the ends, and this thing could rotate about a point in the middle of this vertical pipe. And we had a string wrapped around that pipe, and that string went over a pulley, and on the end of the string we just hung different masses, and so the weight of these masses caused there to be a tension in the string, and that tension was an outside force exerted on this system. And the string wasn't exactly at the middle of the system, like around the pivot point. It was a little distance, about a centimeter away. And so that force, this tension force, was exerting a torque on our system, causing our system to spin faster and faster and faster. Its angular velocity was changing, and we had a way of determining the size of its angular acceleration measured in radians per second for each second. So just a quick reminder, in order to figure out the approximate size of the torque, we had to figure out the size of tension. And remember, torque is the radial distance times the force applied at that distance. And so that string was about a centimeter, specifically 0.01067 meters away from the point of rotation. That's kind of like the middle of the pipe looking straight down. And the tension was basically the size of the force of gravity, the weight of this hanging mass, which is equal to mg. Now, in reality, if we're looking at the forces on this mass, if this mass is starting to speed up on its way down, the force of gravity has to be a little bit bigger than the force of tension. But this is such a small acceleration that these two forces are basically equivalent. And so this is an estimation that we used. We said the force of tension is equal to the weight of the hanging mass, and we use that force to calculate the torque applied to the system. So that's how we found the torque. Taking the radial distance, this value, times mg. To find the angular acceleration, as you can see in the animation down here, we started this from rest, so it had an initial angular velocity of 0, and then we let it spin through a set amount of angular displacement. So we let it spin 1 full time or 2 full times, and so it either had an angular displacement of 2 pi radians for 1 full rotation or 4 pi radians for 2 full rotations. We then timed how much time it took for that to go through 1 full rotation or 2 full rotations, so we then knew the initial angular velocity, the angular displacement, and the measured time. And if we use this rotational kinematics equation, we could use this to solve for angular acceleration, since that's the only thing we didn't know. So solving that for angular acceleration, we get that we can estimate it by taking twice the angular displacement divided by that measured time squared. And this would basically give us one data point. So for a given applied torque, what the resulting angular acceleration was of the system. So we had to do that for 6 to 8 different data points, because we needed to apply small torques, medium torques, and larger torques, a spectrum of 6 to 8 different torques from small to large, basically by adding different amounts of mass. So it caused different amounts of tension, which applied different amounts of torques, which would lead to different angular accelerations. So after using 6 to 8 different masses, we would eventually have the 6 to 8 different torques applied and their angular accelerations. We would then plot torque on the y-axis and angular acceleration on the x-axis to find out, well, graphically how they're related, and also come up with an algebraic representation for how torque is related to angular acceleration. So from this graph, remember, if it's linear, add a linear fit, and then we can basically find out what that algebraic equation is to talk about the meaning of the slope and or the significance of the y-intercept. If it wasn't linear originally, you have to re-express that graph to make it look linear so that we can add a linear fit to get to that final general algebraic equation. So let's look at some results that you guys found and talk about the implications of those results and what we can conclude about the relationship between these two variables. So here are 4 whiteboards, graphs, and resulting equations. And so let's take a look and compare the graphical shapes, the values of the slopes, whether or not people decided to include y-intercepts in their equations. And it should be first apparent that all four groups found a linear relationship between the applied torque and the angular acceleration. What are some other things that we can observe? Well, it looks like at least 3 groups decided to include a y-intercept. One group decided it was relatively insignificant. And if we look at the slope values of our linear equations, we've got 0.271, 0.145, 0.123, and 0.224, so a range from as low as 0.123 to as high as 0.271, and should get similar units. Units of, on the y-axis, so torque units divided by angular acceleration units, so Newton meters divided by radians divided by seconds squared. Those would be the units for our slope. So let's talk about the y-intercept. At least 3 out of the 4 groups decided that maybe the y-intercept is significant, or possibly not. Well, let's think about logically. Would we expect there to be a y-intercept? Well, usually we think, well, what would be true if the x-axis variable, which is the angular acceleration, is 0? What would we expect to be true for the y-axis variable? So if there's no angular acceleration, we would expect that, well, maybe there wouldn't be any torque applied. Or if you didn't apply a torque, we would get 0 angular acceleration. Now that's true, but let's think about it a little bit different way. Group D shows a fairly significant y-intercept, and let's try to think through what that would mean if the y-intercept is significant, and then see if that makes sense. And so let's not think about an angular acceleration of 0, where it's not spinning and stays not spinning. Let's think about what does this equation, what does this graph suggest is true in order to have a very small angular acceleration. So let's say in order to get an angular acceleration a little bit bigger than 0, this suggests, a y-intercept suggests, you have to apply, just to get a little angular acceleration, at least almost 0.02 Newton meters of torque. Or for group C, you'd have to apply a little bit more than about 0.02 Newton meters of torque in order to get a very, very small angular acceleration. So why might you need to apply a minimum amount of torque before there's any angular acceleration? Well, these systems aren't frictionless. And so you guys might have had the experience where you hung a small mass on the end of the string to provide some tension, to provide some torque, and yet there was 0 acceleration. It wasn't enough torque to overcome the frictional torque on the system. So this y-intercept value, if it was significant, seems to quantify the amount of frictional torque on the system. Well, let's think about the slope value now. We have slope values as high as 0.271 and as low as 0.123. And let's just think about looking at the equations, the implications of what does it mean for there to be a higher number multiplied by angular acceleration. So think about it from this perspective. Let's imagine we plug in an angular acceleration of 1. Let's just make it simple. 1 radian per second squared. So if you plugged in 1 for alpha here, this equation would give you how much torque is needed to basically get the system that group B used to have an angular acceleration of 1 radian per second for each second. And for group A, if you plugged in 1, it would again tell you how much torque is required to give their system that specific angular acceleration. And group A, if you plug in 1 here, and let's just, for argument's sake, let's just say that there's not a lot of frictional torque, so the y-intercept is close to 0, but we said it is significant. That would mean group A, to get an angular acceleration of 1 radian per second squared, would essentially need to apply a torque of 0.271 Newton meters. That's what their equation suggests. And group C, let's go down to group C, in order for them to get an angular acceleration of 1, they'd have to use a torque of only 0.145 Newton meters, which is like half the size. So group C required half the torque to get the same angular acceleration that group A did. And if you have to apply more torque to get the same change in angular velocity each and every second, or angular acceleration, group A's system kind of resists angular acceleration more than group C's system does. So let's take a look at the system that each of these groups actually used compared to their equations and their slope values. So group A had this system up here, group B used this one, group C down here, and group D over here. So group A and C have some similarities. They have the same size wood blocks on the end, but actually group A had them all the way in the end. Group C had these blocks a little bit closer to the middle. And groups B and D also had similar size blocks, but they were a little bit smaller than the blocks on group A and group C. So let's just compare A and C first and then get to B and D. So A had a large slope value and C had a smaller slope value. And we said A's system apparently resisted angular acceleration more than C's did. And why? Like, what's different about their setup? Well, they have the same total mass, but it looks like where that mass is located in the system is different. The distribution of mass is different. So for A, more of the mass is farther away from the pivot point than group C. It seems like the farther the mass is distributed away from the pivot point in a system, the more it's going to resist angular acceleration. So maybe this number is kind of a quantitative measure of a system's resistance to angular acceleration. All right, we'll see if that's the case for B and D, if that's also follows the same kind of rule along with the slope value. So we have these smaller masses all the way to the end, and that gave them a slope value of 0.224 with Newton meters divided by radians divided by seconds squared. And for group B, they got 0.123. And you can see that when the masses, these smaller masses were closer to the pivot point than these smaller masses, it did lead to a smaller slope than group D did. And so it seems to fit kind of this idea that we're talking about. So let's take one representative equation and see if we can come up with a general equation which applies to all of our systems to see how algebraically the angular acceleration is related to the applied torque. So we've got torque applied is equal to 0.168 meter newtons divided by radians divided by seconds squared. That's all the slope multiplied by angular acceleration plus some y-intercept value. And remember, we said that this represents the torque applied by friction on the system. So before we go any further, let's simplify these units because that's kind of a mess right there. So we've got meters times newtons, or newtons times meters. That's our units for torque, divided by our units for angular acceleration. And if we simplify this, remember that radians are technically not a unit. They actually represent a ratio. So we've got meters times newtons divided by 1 over second squared. We can put the second squared in the numerator, and we get this. Now remember that newtons can be expanded because a newton is equivalent to a kilogram times a meter divided by second squared. So we've got meters times kilograms times meters divided by second squared, all multiplied by second squared. So we can simplify a little bit by canceling out the second squared, and we get meters times meters, and our slope units simplify to just kilograms times meter squared. So let's rewrite our equation now. We get the applied torque is equal to 0.168 kilograms times square meters, all times angular acceleration plus the size of the frictional torque. Right? We said it took about 0.02 Newton meters or about 0.03 Newton meters of torque applied before there was any angular acceleration. To get to our general equation, I'm going to manipulate this just a little bit. So I'm going to subtract the size of the frictional torque from each side, from the right side and the left side, and it's going to cancel out on the right side, and it turns out that the applied torque minus the size of the frictional torque is equal to the slope times the angular acceleration. And there's really only two torques on our system, one that you were applying with tension and one by the frictional torque that we have to first overcome before there was any angular acceleration. So if we basically add the two torques together, one in the positive direction, one in the negative direction, we're getting the sum of the torques on the system. So our equation becomes the sum of the torque on the system is equal to something times angular acceleration. And we said that the slope, this something, we think is related to the system's resistance to, or hesitancy to have an angular acceleration. Now, looking at this equation, this should look familiar, not because we've seen this equation before, but it's kind of in the same general form as another equation we've used a lot throughout the year. The sum of something is equal to something times something relating to acceleration. Think Newton's second law. Right? Newton's second law is acceleration is equal to the sum of the forces over the mass, or if you solve this for the sum of the forces, we get the equation, the sum of the forces on a system or an object is equal to the mass of that system or the object times its linear or translational acceleration. See how they're kind of in the same general form. So let's see if we can use our understanding of Newton's second law to help us figure out what the slope of our lab equation actually represents. So here's our rearranged form of Newton's second law. And I want us to think about what mass actually represents in this equation, right? Mass is measured in kilograms, right? Use the variable m. But what is it? Well, in this equation, this value of m, as m increases, the size of the acceleration decreases when the net force or the sum of the forces stays constant. So m is kind of a measure of an object's resistance to acceleration, because if m is bigger, acceleration is smaller. Something's resistance to a change in velocity is known as inertia. And this equation is talking about translational motion, movement through space in the x, y, or z direction. And so mass is actually, we could call that a translational inertia. It's the object's resistance to a translational acceleration or a linear acceleration. The more mass you have, the more that object is going to resist being accelerated by a force or by a net force. Well, let's use that same idea to think about this equation right here. So we've got the sum of the torques in the system is equal to something times angular acceleration. This represented something's resistance to linear or translational acceleration. And remember, we thought this kind of represented an object's resistance to rotational or angular acceleration. So if we called this translational inertia, we could call this rotational inertia. Rotational inertia is an object's resistance to angular acceleration. We're going to use the variable I to represent rotational inertia, and the units are just the units of our simplified slope, kilograms times square meters. So our equation then becomes, replacing our slope with I, which represents rotational inertia, we get that the sum of the torques on a system is equal to the rotational inertia of the system times its angular acceleration. And remember, rotational inertia is kind of like the rotational equivalent of mass. And so we could rearrange our general equation to put it in the form kind of that we're familiar with Newton's second law, where we get angular acceleration is equal to the sum of the torques divided by its rotational inertia. And this kind of helps us conceptually think through what's going on with rotational motion. If the net torque increases on a system and its rotational inertia stays the same, we're going to get a bigger angular acceleration. Or if the net torque stays the same and our rotational inertia increases, that means our angular acceleration has to decrease. So we can kind of think through some conceptual related questions just using this equation. So if you're writing a lab report for this, we do have two new terms you'll have to define in your lab report. One is translational inertia. You can see the definition here. And the second one is rotational inertia. For the remainder of the video, I want to talk through two quick examples, kind of a conceptual application of this idea of rotational inertia, and then a quick quantitative example as well. So let's go back to our lab setup for a minute. And we're looking at three different lab setups. Notice they've got the same masses attached to the pipes, but they're at different locations away from the pivot point. And in each case, we've got essentially almost a kilogram hanging off of there. And so we almost have 10 newtons of force of tension on each, which is leading to a certain amount of torque. So they're experiencing the same amount of tension, experiencing the same torque, but they have different rotational inertias. Remember, which one of these things would have the largest rotational inertia? The largest resistance to angular acceleration? Well, it's going to be the one that has the mass that's the farthest away from the pivot point. That's going to be this one right here. And which one would have the least rotational inertia? Well, again, all these things have the same total mass, but where the mass is relative to the point about which the thing rotates matters. Here the mass is closest, so it should have the lowest rotational inertia, the lowest resistance to angular acceleration, so therefore a torque is going to give it the biggest angular acceleration. And this guy over here should have the largest rotational inertia, the most resistance to acceleration, so for the same applied torque, the same net torque, it's going to have a smaller angular acceleration. So let's just do a quick quantitative problem before we finish this video. So imagine we have a merry-go-round, which is brought up to an initial angular velocity of 0.75 radians per second. Maybe, kid gets on here, people push this thing, so it's spinning at a certain angular velocity. And then they stop pushing, and so it's allowed to spin freely until friction or frictional torque brings it to rest. Its final angular velocity will be 0. The question we're going to figure out is, how much time does it take for the merry-go-round to stop spinning? Right after the kids stop pushing, they take 20 seconds, 5 seconds. That's what we're going to figure out. So couple things that we need to know. One, the merry-go-round and the rider have a combined rotational inertia of 200 kilogram meters squared. This is that quantitative measure of how much the system of the kid and the merry-go-round together resist slowing down rotationally or speeding up rotationally. And friction exerts a torque of negative 30 meter newtons. Okay, so we're going to assume that this thing is spinning initially in the positive rotational direction, and torque is going to be exerting, or friction will be exerting a torque in the other direction. That's what we're going to call it, negative. So whenever we solve motion problems with forces, whether it's translational motion, rotational motion, forces or torques, just write down all the things you could possibly know before we start thinking about equations. So these are the different variables which can describe rotational motion: angular displacement, initial angular velocity, final angular velocity, angular acceleration or time. And then these are the things related to explaining why things have angular accelerations: the net torque on the system, or the sum of the torques, and I, which remember represents the rotational inertia. So angular displacement is not given. We don't know how many times it spins around or the radians it spins through while it slows down. But the initial angular velocity was given as 0.75 radians per second, and we're assuming it's in the positive rotational direction. It's coming to rest. So in the end, the final angular velocity should be 0 radians per second. We don't know what the angular acceleration is. We are going to be solving for time, so that's another question mark. The net torque is the sum of all the torques on the system. Well, the problem is happening. Goes from this initial angular velocity to rest, essentially, with only a frictional torque applied. So the only torque on the system is friction. So the net torque is just the size of the frictional torque, size and direction of the frictional torque, negative 30 Newton meters. And we're given the fact that the combined rotational inertia of the system as a whole is 200 kilograms square meters. So let's first start by finding the angular acceleration of the system. Like, initial velocity, angular velocity, and the final angular velocity is not enough to figure out how much time it takes to go from one angular velocity to the other. So let's find out what the angular acceleration is first. So let's use the equation we just developed in lab. Angular acceleration is equal to the sum of the torques over the rotational inertia. And we have both of those values. So it's just negative 30 meter newtons, or Newton meters, divided by 200 kilograms square meters. So we get negative 30 divided by 200 gives us negative 0.15. And if we ended up expanding this to kilograms times meters over second squared, cancel everything out, it turns out we'd only end up having 1 over second squared for units. But we're solving for an angular acceleration, so we're going to write radians divided by second squared. Because remember, radians are technically not a unit, so we can just throw that in there because this is an angular acceleration. So we now know alpha. So the last thing is, let's find the time to stop spinning. If we know the initial angular velocity, the final angular velocity, and now the angular acceleration, we just need an equation that has all 4 of these variables here, including time. If we know 3, we can solve for the 4th. That is our first rotational kinematics equation. Final angular velocity is equal to initial angular velocity plus angular acceleration times time. So we plug in our final angular velocity of 0, our initial angular velocity of 0.75 radians per second, our angular acceleration of negative 0.15 radians divided by seconds, or radians over seconds squared, multiplied by our unknown time. So we're going to subtract 0.75 radians per second from each side, and then divide by negative 0.15 radians per second squared. Do a little bit of algebra to solve for time. Time turns out to be just 5 seconds. So with this video, you guys should now have an understanding of rotational inertia conceptually and quantitatively, and now have a new algebraic tool to solve rotational motion problems.